Bond angle. Bond angle is the angle between atoms bonded to the central atom. So when we're talking about bond angle, what we're referring to again, it's specifically the angle that exists between atoms in a molecule that are bonded to the central atom of that molecule. Let's look at an example such as the molecule SF6. This would be our Lewis structure we have for the SF6 molecule. Our SF6 molecule has 6 things attached to the central atom. We need 6 orbitals to hold our electron pairs, so this will use the sp3d2 hybridization scheme. sp3d2 has an orbital geometry of octahedral. Each orbital holds a pair of electrons. In this molecule, each pair of electrons is a bonding pair of electrons, as a fluorine atom is covalently bonded to the central atom by each one of the orbitals in our octahedral orbital geometry. The molecular geometry in this case is also octahedral. When we refer to bond angle, that's our angle between our atoms that are bonded to the central atom. In this case, these two atoms in the plane of the square of our octahedral, our angle between the atoms is 90 degrees. We'd say the bond angle is 90 degrees. Between the fluorines on the top, this one extending straight up from the plane to this one in the plane of our square, the bond angle is also 90 degrees. The bond angle, again, is the angle measured between atoms that are attached to the central atom in the molecule. Let's do another example, the molecule ClF3. Here's our Lewis structure for the ClF3 molecule. You can see we have 5 things around the central atom. Consequently, the central atom hybrid scheme we need is sp3d. The orbital geometry we'll use is the trigonal bipyramidal orbital geometry. The trigonal bipyramidal orbital geometry has 3 orbitals in the shape of a triangle in a plane, and 1 more orbital sticking straight up and straight down from the plane. Each orbital again contains a pair of electrons. 3 of the orbitals are bonding pairs of electrons. 2 of the orbitals are what we call unshared pairs of electrons. This molecule is what we call a T-shape. We go through the atoms in the molecule, and it's only the atoms where we'll measure the bond angle. You can see our bond angle here is going to be 90 degrees. On the top part of the T, our bond angle is 180 degrees between the bonding fluorine atoms. In a molecule such as this, which has unshared pairs of electrons, there's no bond angle between unshared pairs because the unshared pairs are not a bond. Bond angle is only measured between atoms that are bonded to the central atom. Let's look at another example, the molecule CH4. CH4's Lewis structure shows us that we have 4 things around the central atom. We need sp3 hybridization, and the orbital geometry is tetrahedral. Each pair of electrons in methane is a bonding pair of electrons. In a tetrahedral molecular geometry, our bond angle is going to be 109.5 degrees between any of the bonding atoms, and that all of the bonding pairs are equally spaced according to the valence shell electron pair repulsion theory. Change our example to a molecule of ammonia, NH3. Our Lewis structure for ammonia also shows we have 4 things around the central atom. We're going to need sp3 hybridization, and the orbital geometry is tetrahedral. However, ammonia's bond angle will be slightly different from what we saw in the previous example of methane. The ammonia molecule has 3 pairs of bonding electrons and 1 unshared electron pair. The bonding pair of electrons are held by two sets of protons because there's two nuclei holding on to a shared pair of electrons. The protons in the nucleus of the nitrogen atom and the protons in the nucleus of the hydrogen atom are both hanging on to the bonding pair of electrons just being shared between the two atoms of nitrogen and hydrogen. On the other hand, the unshared pair of electrons is only held by one set of protons. One nucleus is hanging on to the unshared pair of electrons. It's only the protons in the nitrogen atom that are holding on to the negatively charged pair of electrons in the unshared pair. The consequences of this are, we have therefore the electron cloud of an unshared pair of electrons is going to be larger than what we see for the electron cloud of a bonding pair. Since the unshared pair is being held by only one set of protons in one atom's nucleus, what happens is the cloud can expand out slightly relative to what happens to the electrons in a bonded pair of electrons, where the electrons are being held by not one, but two nuclei. Because the unshared pair of electrons is now taking up more space, that means another part of the molecule has to take up less space. The unshared pair causes the other bonding orbitals to pinch down slightly. Since the unshared pair is taking up more space, the bonding pairs now pinch down and take up less space between the bonding pairs. The bond angle is no longer the 109.5 degrees we'd expect to see in a tetrahedron. Instead, the unshared pair causes the bond angle to pinch down by 2 degrees, and we see a bond angle in ammonia of 107 degrees. The molecule water shows a similar deviation because of unshared pairs of electrons. Our water is also sp3 with an orbital geometry of tetrahedral. And our water molecule, you can see water has two bonding pairs of electrons. And our water also has two unshared pairs of electrons. The geometry of water is described as a bent molecule with all the electron pairs repelling. We get a bent geometry. And in water, again, our bond angle does not equal 109.5 because our unshared pairs of electrons, since they take up more space by virtue of being held by only one nucleus, since they take up more space, they cause the bond angle to pinch down slightly in our water molecule. Instead, the observed bond angle in a water molecule is about 105 degrees between the bonding hydrogen atoms. The effect of unshared pairs taking up more space and pinching down other bond angles is typically only of concern for bond angles less than 120 degrees. Which means it's primarily only of concern when we have a tetrahedral orbital geometry. Not exclusive to this, but that's mainly where this phenomena is seen, of unshared pairs taking up more space and pinching down other